Okay, we're on lesson 6.4, the fundamental theorem of calculus. So before we go there, we're going to kind of refresh our ideas of using LRAM, RRAM, and MRAM to estimate our area, right? So find the Riemann sum. Riemann sum is just a very fancy way of saying using rectangles to approximate the area. Now you're going to notice that this approximation is slightly different, but we've done this before, where our intervals are not equal distances. So you're going to see that the partition is separated differently, and you're going to have to follow what it says in the directions on how to separate your partition. So first thing we're going to do is draw x squared minus 9 on the three graphs provided here, because we're going to do LRAM, RRAM, and MRAM respectively on each of the graphs here, okay? Okay, so when you are done with the graph here, then put in your x-axis to figure out that your area that you're looking at is always between the x-axis and the function itself, right? And then finally, looking at the partition given to me, we know that we're really looking at the area between -1 and 6. So we're going to put in -1 as my original lines and 6 as my other line to trap my function here. So -1 and 6. And don't forget to kind of shade in your region to look at what is the area we're really looking at. So I would suggest using a much lighter color of highlighter to shade this in, so you know that the area I'm looking at is this piece here. And quickly do that for all three graphs. Okay, now let's use LRAM to do the first one. So it says use the left endpoint, and the first width I'm looking at is only between -1 and 0. So between -1 and 0, I'm using the left endpoint here. That will help me draw my first rectangle here. So that's my first estimation. The second set of width is 0 to 2. So my second rectangle is 0 to 2. Still using my left-hand side to draw my rectangle. That will be my second approximation. Next rectangle is from 2 to 4. This is where it gets a little tricky. 2 to 4, you see how it is both below and above the x-axis. So you still want to stick to your left endpoint. So use your left endpoint here to draw your rectangle. And the last approximation will be from 4 to 6, using the left side to draw my rectangle. So if it will help you, I would strongly recommend to kind of shade it in. Sorry, it's a little too big. To shade it in and kind of see the difference between your approximation versus your actual graph. So this left endpoint approximation is not perfect. It's not the best actually, but this is what you can see. This is what our approximation would get us, okay? All right, we're gonna do the same thing for our right endpoint. So the same width as before, so 0 to 1, but now from the right-hand side, so it's gonna be this approximation here. Then from 0 to 2, go to the right endpoint, draw my rectangle there. From 2 to 4, go up to my right-hand side, draw my rectangle this way. And then last but not least, between 4 to 6, go up to my right-hand side, draw my rectangle. This is my approximation. You can see, yes, it is way overestimate, but this is kind of the way our approximations go, right? Some things are grossly overestimate, and some are grossly underestimate. Will we ever get a better estimation? Yes, we will. We'll definitely have more methods later to have better approximations, right? All right, last one, don't forget MRAM, right? Some of you struggle with this on the quiz, so make sure you look between -1 and 0. This is my width. You go up the middle, right up the middle, right here, that is where you're going to draw your rectangle, okay? So I'm going to get rid of my dots because I don't want them there. But that is your midpoint. You go across like so. That will give you your very first rectangle. Okay. Between 0 and 2, you go to the 1. 1 is in between, so 1 is going to create your height this way. All right. Between 2 and 4, you don't have any height because the middle point is right here. That is a 0, so no height for that one. And then the last one will be using the height of 5 to draw your rectangle from 4 to 6. So that would be the final estimation. And again, to just kind of highlight that, make sure you can see the difference between your LRAM and RRAM and MRAM approximations for this particular graph. Okay, and then don't forget, we got to figure out our answers, right? So for me, first thing I'm going to do is I'm going to put in my t-table, because the t-table will be really helpful in terms of figuring out what is the value I really want. So if my t-table, I'm going to put in all the values I see here. So -1, 0, 2, 4, 6, right? So these are the partitions they gave me. So go ahead and plug this in. I get 1 squared is -1 squared is 1, minus 9, that's -8. That's -9. 2 squared is 4. 4 minus 9 is -5. 4 squared is 16. 16 minus 5 is 7. And then 6 squared is 36. Minus 9 is 27. Don't forget, we need a second t-table because we need that MRAM, right? So for a second t-table, between -1 and 0, we get -1/2. And I have 1, I have 3, and I have 5, right? So I'm going to do the easy ones first. 1 squared is 1, minus 9 is -8. 3 squared is 9, 9 minus 9 is 0. 5 squared is 25, 25 minus 9 is 16, all right? So what about the other one? That's -1/2 squared, so 1/2 minus 9. Well, 1/2 squared is 1/4. 1/4 minus 9, you get 1 minus 36 over 4, so -35 over 4, okay? All right, so now let's go ahead and answer the questions because we need our approximation, right? So part A for LRAM, and then part B for RRAM, and part C for MRAM. So for LRAM, I get a rectangle of 1 times the left endpoint, so -8, and then a width of 2 times -9, and a width of 2 times -5, plus a width of 2 times 7. Just like before, we don't use the last endpoint, so we don't use that 27, right? So -8 minus 18 minus 10 plus 14. All right, this is going to be really lazy. Grab out my calculator and figure this out. So I get 14 minus 10 minus 18 minus 8. I get a total of -22. Remember, -22 doesn't mean it's negative area. It just means that the area is below the x-axis, right? Or mostly below the x-axis. Okay, RRAM, my first rectangle still has a width of 1, but now I use a height of -9. Width of 2, I use a height of -5. And then 2 use a height of 7, and 2 use a height of 27. So I get -9 minus 10 plus 14 plus 54. So I get 54 plus 14 minus 19. I get an approximation of 49. That's very much an overestimate, right? Okay, how about MRAM? So, oops, too many M's, apologies. All right, MRAM, width of 1 times the height of -35 over 4, and then width of 2 times -8, width of 2 times 0. We don't really need that, but putting it there so you can see it's not gone. So -35 over 4 minus 16 plus 0 plus 32. So that's really 32 minus 16. That gives me 16. So -35 over 4 plus 16. That's -35 plus 64 over 4. 64 minus 35 gives me 29 over 4. I think this is a much better estimation. So that's just a quick reminder of how to use LRAM and RRAM with different width of partition. So what is the whole point of this? Well, the whole point of this is to remind you that in calculus, we really should have an exact way of figuring out things. So we're now combining the idea of integrals as antiderivatives and integrals as an area under the curve. So when you're doing antiderivatives, you usually have a plus c, right? Well, now we have what we call definite integral. I'm looking at the integral with a beginning and an end, like I normally do right here, a beginning and an end, right? So how do I do something like this? Well, you will start off the exact same way as before. We're going to take the antiderivative, okay? So taking the antiderivative of this, let's see what we will get. So we're looking at this, the antiderivative, I get 2x, that's 2x squared over 2, plus 3x. Now, that minus 4 is a coefficient. That's really negative 4 times 1 over x. Now, keep in mind, what is 1 over x? You can't use power rule with 1 over x, because 1 over x is x to negative 1. If you use power rule, don't you add 1 to the power, which makes it 0, and then you divide by the new power? That doesn't work. So x to negative 1 power, x to negative 1 power has a very special property. The integral of x to negative 1 power, or integral 1 over x dx, is really natural log of x. And we need to put absolute value around it, because the natural log of anything, natural log of the argument cannot be negative, or it can't be negative, it can't be 0 either. So the absolute value will take care of most of the situations. So in this case, this is really 4 times the natural log of x, okay? Now, once you've taken the antiderivative, and by the way, please make sure you write this down. This is one of the rules that wasn't in the chart before in the last lesson, so make sure you add it to the table of derivatives, antiderivatives that you need to memorize, all right? Another one that's handy to have, which wasn't on your chart, apologies, is integral e to the x dx. And you've done this before because it is just e to the x, right? Oh, plus c. Don't forget your plus c's, all right? Because the integral of e to the x is e to the x, the derivative of e to the x is e to the x. What if there's other things in the exponent? We'll take care of that later. Right now, this is the most base form. The base form is e to the x, the derivative, the integral is all e to the x, okay? I'm gonna erase this so I can have more room. So make sure you have this written down, or at least rewind and get all the information down, okay? All right, so now I have taken the antiderivative. What next? Why didn't you put a plus c? Because this one has a definite integral. It tells me it goes from 1 to 5. So then the notation is to put a bracket like this and remind myself I'm going to plug in 1 and 5. So the way to do this, looking at over here, right? When you take the integral, you take the antiderivative. That's why the little f becomes big F. And you got to plug in the b and plug in the a and subtract each other. So plug in the b, top minus the bottom. Always, always, always. So then my next step is to plug in the 5. So I get 2 times 5 squared over 2 plus 3 times 5 minus 4 natural log of 5, right? That's the first plug-in, minus, plug in the 1 now. 2 times 1 squared over 2 plus 3 times 1 minus 4 natural log of 1. Okay, the rest is algebra. You got to clean this up. So I get 25, because the 2's reduce out, plus 15 minus 4 natural log of 5, fine, minus 2 over 2, that's minus 1, minus, to distribute the negative, 3, and then plus 4 natural log of 1. Now, if you recall, natural log of 1 is 0, so that's actually gone, right? So now we just clean up and go 25 plus 15, that's 40. 40 minus 4, that's 36. So 36 minus 4 natural log of 5. And that would be a perfectly fine answer. Some books don't like the coefficient. Some books, some tests don't like coefficient in front of the natural log. So some texts will remind you that, hey, this is really natural log of 5, and they move the 4 as an exponent up here to rewrite it as 36 minus natural log of 625. So just keep in mind, these are exactly the same. They're the exact same thing. Is one better than the other? Not necessarily, but if it is a multiple choice test or quiz, you have to recognize that they are the same answers, okay? All right. Same thing, next one. We start off by looking at it as an antiderivative. So remember what I said about coefficients. You can put the coefficient outside. So if you want, you can go ahead and do it this way. You can look at it as 4 integral 0 pi over 3 secant x tangent x dx. All right, that way you can take care of the 4 later. The 4 stays out here. And I know that antiderivative of secant tangent is secant x evaluated from 0 to pi over 3. So the 4 still stays out here, and now I can plug in secant of pi over 3 minus secant of 0. Right, I can work with those and then take care of the 4 outside. Okay, secant is 1 over cosine, so what is the cosine of pi over 3? Cosine of pi over 3 is 1/2. Secant of that is 1 over 1/2, so that makes it 2. Minus secant of 0. Secant is 1 over cosine. Cosine 0 is 1. 1 over 1 is 1. So 4 times 1, my final answer is 4. Okay, all right, continue. Next problem, you have 1 plus 2 cosine x. So antiderivative of 1 is x plus 2 cosine x. So integral of cosine is positive sine x. E value is 0 to 3 pi over 2. This is why it's important to know your unit circles, because we're now plugging in things, right? So 3 pi over 2 plus 2 sine of 3 pi over 2. Excuse me. Minus 0 plus 2 sine of 0. All right, so we got lucky because 0 is gone, sine of 0 is gone, so those are gone. And so if we clean this up, we get 3 pi over 2 plus 2. Sine of 3 pi over 2 is negative 1, so my final answer is really 3 pi over 2 minus 2. That's my final answer. Okay. All right, what about something like this? We have a fraction and our exponent. We did this once in our notes, and hopefully you did more in your homework. So you have x to the, you add 1 to your power, so 5 over 2. Now, instead of dividing by 5 over 2, we multiply by the reciprocal. So multiply by 2 over 5, e value is 0 to 5. Again, that 2 over 5 is really a coefficient. You can take it outside and then looking at the evaluation of just 0 to 5 on its own. So 2/5 out here, and you have 5 to the 5 halves minus 0 to the 5 halves. Right. Now, again, 0 to 5 halves is gone. That's 0. So this answer is not really clean. Well, you can clean this up. 2 over 5, 5 to the 5 halves is really 5 to the 5th square root of that. So what that means is there's 5 5s in there, right? So really that's 1, 2, 3, 4, 5 square root. So you have 1, 2 pairs. So you really can pull out 5 times 5 and then root 5, right? To clean up this term here. So that way one of your 5s will reduce out nicely. And your final answer is 10 root 5. That would be your final answer. Okay. All right, that was number 5. We'll be on to number 6. Okay, so when you have something like this, you have to keep in mind that when you're taking the derivative, when you're taking an integral of something like this, you are, there's chain rule involved. So another way to remind students of this is that when you're taking the derivative, right, it's saying find dy dx. So I'm asking you, this is y is given to you as this function. Take the derivative of that. So I'm saying take the derivative dy dx of this function. Now, we talked about this earlier that, hey, doesn't the derivative and integral kind of cancel each other out? So what about this 2x and this 0? What does it do? Okay, so write yourself a note. When this is happening, when you're taking d dx of an integral a to b of a function, and it's usually dt, right? Because it's a different variable here. You're plugging it in and you're dealing with chain rule. So the best thing about this is that because the derivative and the integral cancel each other out, you actually don't have to change the function itself. So it still remains as a lowercase f. If you need to take the antiderivative, it becomes a capital F. So it's a lowercase f, and you simply plug in the b value. But because you're taking the derivative, you have to keep in mind chain rule. So you need to take b prime, the derivative of b, right? And then same thing, plug in the a value down here because you're still doing the derivative and the antiderivative here. And then keep in mind the chain rule a prime. So this is a very important thing. Oops, didn't go far enough. This is a very important thing to have. So make sure you keep that in mind because that is super, super helpful when it comes to dealing with a problem like this. Okay, so I say dy over dx is equal to, keep this, cosine of 2x, and plug in the 2x in there. Then what is the derivative of 2x? 2 minus cosine of 0. What is derivative of a constant? 0. So that's awesome because typically that second term, because it's a constant, goes away, it becomes 0, right? So now all you have to do is clean this up. And usually I put the 2 on the front to remind myself it's really cosine 2x times 2. Okay? All right. So sometimes they don't all clean up that nicely. So let's see how this next one goes. So dy over dx equals, so f of b, so that cosine x squared times the derivative of cosine x. So you got to keep in mind, derivative of cosine is negative sine x, right? Minus, all right, plug this in now. So sine x squared. What is the derivative of sine x? That is cosine x. All right, so let's see if we can clean this up a little bit, right? excuse me, I get negative cosine square x sine x minus cosine x sine square x. So because it's derivative, I usually want you to factor out as much as possible. But factor out cosine x and a sine x, you'll leave yourself with cosine x plus sine x. That's about as much as it will clean up. So that's that would be our final answer. Okay. All right. That's it for the fundamental theorem calculus. So it's just a really fancy way of saying take the antiderivative, but now plug in your b, plug in your a, and subtract each other. That's what the theorem is. Okay. All right. That's it.